Okay, so in this video, I want to talk about where the equation for the distance between two planes comes from. And in reality, you can also use the same formula for a distance between any plane and another point in space. So I've drawn two planes here. We're looking at them from the side. So they would be extending into the paper. And I wrote two equations here. These are the general linear equations for a plane. They would not be the same in this case, and actually we'll label this one D0 and D1, just to make sure you guys know that. And then, if I want to find the distance between these two planes, I can imagine the shortest distance between them as one that is perpendicular to each of them. And these are parallel planes. Please note that if you want the distance between two non-parallel planes, that distance would change over time, but eventually would be zero at some point because they would intersect. But let's say I have a point on plane 1, let's call that P0, and that's X0, Y0, Z0, and some other point over here on plane 2, okay, we'll call that X1, Y1, Z1. Okay, well, I could very much find the distance between these two planes by taking a vector, or excuse me, these 2 points, vector, let's call it this way for sake, you could do the other way though too, and finding the magnitude of that vector. And I'm going to call that vector V. Okay? But that doesn't give me the distance directly between the two planes. So that's not quite right yet. But if we think back to doing some kind of projection or a component, we could project this vector V onto the normal vector here, which I will call N. Okay? And that would give us how much of V is actually going in this direction. Okay? That component or scalar projection would give us the real distance in between these two parallel planes. Okay? So let's remind ourselves what the component would be. So we're kind of saying here that the distance is the same as the component of the vector V onto the normal vector. And notice that this is the same normal vector for both planes. It might not be written that way in the equation, but they're definitely either scalar multiples of each other or they're the same vector. They can be described as the same vector. This formula is N dotted with V over the length of N. Okay? And I know that there are some other formulas we could use for the component of a vector, but we don't have any angles here and I don't really want to find them. This is nice because I do have components for these vectors. Okay? And remember that in an equation of a plane, okay, the normal vector provides us our kind of A, B, and C, those kind of direction numbers. Oh, you can't see what I wrote over here. So don't forget, N is A, B, C. And V is this vector right here. Scoot that over. So V is the vector x1 minus x0, y1 minus y0, z1 minus z0. And I kind of went off the page there, but these are our two vectors. Okay, so if we were to fill in this formula, what I'm going to do is get, okay, oh, and I forgot one very important thing. What do we know about distance? Well, distance cannot be negative. So I'm going to say that we should be the absolute value. The magnitude of n will always be positive, considering it's a square root formula, but I want to make sure that the other parts are positive too. So just to make sure we get a real life answer, distance cannot be negative, we'll take the absolute value. Okay, so n dotted with v, that would be absolute value a times x minus x0 plus b times y minus y0 plus c times z minus z0. All right, all divided by the length of n, which is the square root of a squared plus b squared plus c squared. Okay, well, we're starting to get there. We're starting to get to that formula that looks like the one in our notes. So if I do a bit of distributing, let's see what I get. So ax, and I'm going to combine, oh, this is supposed to be x1, y1, z1, okay? I'm going to combine all of the x1 terms to the front and all of the x0 terms to the back. So ax1 plus by1 plus c z1 minus, I'll distribute that negative, ax0 plus by0 plus c z0 all over that same square root formula. Okay, now here is where this right here could be equal to this d0 right here. Okay, and that's great. But you're thinking to yourself, okay, well, this could be equal to d1, and you're right. Okay, this formula can be simplified to be d1 minus d0. Okay, because don't forget, these general formulas came from the fact that d0 was minus a times x0 minus b times y0 minus c times z0. Okay? Now, if I skip directly to this step, I missed something, a very important qualification. Because you're like, Miss Kelly, why didn't you just give us this formula in class? I want you to notice one thing about these two planes. I used A, B, C as their direction numbers. That means I used the same numbers, A, B, and C, to describe both planes. That's not always the case. Okay? So I can only use this formula when the A, B, and C are the same in both planes. Now, there's a really easy way to do that. You could make them the same by multiplying one equation by some scalar, because if I multiply this side, it'll still be 0. So I can multiply one by another to get a scalar. Okay, and I want to show you, in the notes, you'll find that I did example number 10 one way. I want to show you another way using this formula. Okay, so remember, the equation in the notes works as long as you use the normal vector for one plane and a point in another plane. But this makes it a little simpler if the direction numbers are the same in both of them. Okay, so for example, in example 10 from the notes, from 11.5, 11.6, okay, we asked you to find the distance given these parallel planes, 3x plus 6y minus 9z equals 4, and x plus 2y minus 3z equals 1. So you can see right away that I couldn't jump right to using this formula because the A, B, and C are not the same. Now, they are parallel vectors because these normal vectors are parallel because they are scalar multiples of each other. Okay, but in order to jump right to this formula, okay, we would need to multiply this one by a scalar. Okay, so I'm going to multiply this one by 3. Okay, so that means I could describe this plane also as 3x plus 6y minus 9z equals 3. Okay, now I have the same A, B, and C. A, B, and C. Okay, so if I look at D, okay, which in this case, D, well, right now it's not in the right form, so I got to move that D to the other side. So 3x plus 6y minus 9z minus 4 equals 0, and 3x plus 6y minus 9z minus 3 equals 0. Now it's in the right form. So now I can see that this is like D1 and this is D2, or excuse me, this is D1 and this is D0, however you label your planes. And no matter which A, B, and C I use, I will plug in the same. Okay, so the distance between these two planes is the absolute value, -4 minus -3, all over the square root of 9 plus 36 plus 81. Okay, in the numerator, I'm getting -4 plus 3, which is 1. Well, -1, but take the absolute value. I'll write that. In the denominator, I'm getting the square root of 36 plus 90, which is 126. Okay, so maybe my final answer is 1 over square root of 126. No need to simplify that radical. Okay, and you'll notice, let me pull out the notes from over here. Okay, here's example 10. I got the same thing. I tried to simplify it a little bit more for you guys, but here I got the same exact thing. And instead, here I use the direction vector 3, 6, 9, and then use -4. But I used a point 1, 0, 0 that was on the other plane. Okay, so we end up with the same formula, however you want to think about it. But let's recap. This distance formula works because we are taking the distance between 2 points, one on one plane, one on the other. Okay, we're creating a vector v in between them, and we're projecting that vector onto the normal vector between the two planes. Okay, the reason we were able to use d1 and d0 in this example was because the normal vector was the same for both of them. However, that's not always true. Okay, and so you can manipulate one of the equations of the planes so that they have the same normal vector components. Or you can use the example in the notes where you just pick one of them and a point on the other plane to plug into the original formula. And that original formula, let me write it one more time for you here, is that the distance is equal to the absolute value of ax plus by plus cz plus d all over square root of a squared plus b squared plus c squared. Okay, and remember this x, y, z is on the opposite plane from the one that has the normal vector a, b, c.